Boa tarde a todo mundo, sejam bem-vindos no Café Geológico. Hoje eu tenho o prazer de apresentar a nosso apresentador, o professor Kerry Gallagher. Kerry é professor no Departamento de Geociências da Universidade de Rennes, na França. Ele é geofísico e fez sua doutorado na Universidade Nacional de Austrália, em Canberra, e depois fez pós-doutorados na University College of London y la Universidad de Melbourne, en Australia. Y finalmente trabajó por 13 años como profesor en un Imperial College en Londres hasta 2007 y desde 2007 profesor en la Universidad de Rennes. Entonces, Kerry, muito obrigado pelo convite. Now, of course, speak in English and the stage is yours. Okay.
Boa tarde. Obrigado por me convidar para dar seminário. I hope you understood that. Okay, so I'm sorry I don't speak Portuguese as well as I should. It's a pleasure to be here. So I've been here a few times in the past. It's always a pleasure to come to Brazil, São Paulo. So could you, was it me who does that? Ah, okay. I'm not paid enough to do this.
Okay.
Okay. Yeah. Okay, well, if I have to be here, maybe I'll take this down there. Is that okay if I'm here?
Yes.
Move the camera.
Just move.
Okay, so this is what I'm going to talk about. It's not the most exciting title that you could ever imagine. And I'm going to talk about two little examples of doing exactly this, how we try and estimate heat flow in the past. Before I start, just some of you maybe don't know where Rennes is. I do move around a lot, so you're going to so here's France, here's northwest France. Paris is sort of here somewhere. And this is Rennes in the northwest of France and Brittany. You probably guess I'm not French, but my name suggests where I might be from. In fact, Kerry here, my first name, is a part of Ireland. So this is the Republic of Ireland here. Kerry is this part here in the southwest, where my mother's family come from. And Gallagher, my surname, second name, is a name very common up here in the northwest of Ireland in Donegal, which is still in the Republic of Ireland. It's sort of a relatively wild part of Ireland. And in Irish, this is what my name looks like. So if any of you can say that, I'll be very surprised. I can't say it. So this name actually means, in Irish, means mercenary, or a foreigner who came to fight a long time ago. So this is very difficult to say. So what I'm going to actually talk about after this will seem very easy compared to that. So I'm going to give a little bit of background of how we do this kind of thing. I'm not going to go into a lot of detail. I don't really have time. I'm just going to give you two examples of estimating Paleo-heat flow in onshore East Greenland and offshore northern Norway. Okay, so the word Bayesian, sorry, some of you have already seen this more or less, I'll explain that very quickly. So it's nothing really new. It was a paper published in the 18th century, not even by Bayes himself, but by his friend. The idea between Bayesian modeling is we deal with probability distributions rather than just one model. So we're not really interested in looking just for a best model. We're looking for a whole group of models, a distribution of models. And we have this little relationship, which is called Bayes' law or Bayes' theorem, which says at the posterior, which is a probability distribution here, the posterior, which is the solution to our problem, is proportional to something called the prior. And the prior is also a probability distribution, which depends on what we think we believe, often including geological information if we need to. The posterior proportional to the prior multiplied by the likelihood. And the likelihood is really a measure of how much information there is in the data to tell us about our model. And effectively, the likelihood transforms the prior into the posterior. So the likelihood could be a probability distribution. It doesn't really have to be. It can be. And the idea, we say what we think about some problem, what's reasonable. We collect some data. The data tell us something perhaps different, how we change our opinion of what we think. And then that lets us calculate a posterior, which is sort of the solution to our problem, starting with from where we thought at what we thought at the beginning. And we'd hope that the data dominate the posterior. So the prior shouldn't be too important in determining our solution. So a little example of this is sort of from a paper. We're talking about temperature history modeling. So just a one-dimensional function. Temperature is a function of time. And to try and demonstrate the idea of Bayesian modeling, let's say here we've got temperature going down to 140 degrees, time going from 100 million years to the present day. And let's say we think that temperature can be anywhere in that box. So it's a one-dimensional function of time, and it can go anywhere. We don't know. So that red box is our prior. It's what we think is reasonable. It's a 1D function, can be anywhere in that box with equal probability. And then we collect some data that maybe are sensitive to this temperature history, which is a bit what we're going to look at in a minute anyway. And we say, what do those data tell us about where we should be in that box? So it might be something that looks like this, where the red colors are basically higher probability. So think of a probability distribution, higher probability, and blue is low, and white is not at all. So the data, if you like, we could be anywhere in here, and the data have told us some things that we can't be here where it's white. The red tells us we really want to be doing this, going from high temperature to low temperature. And we have some information about what happened earlier on here, but not a great deal. So the well-resolved parts of the model are here. So that's the posterior. We've transformed. I haven't shown you the data. We have some data which tell us that, which updates what we thought originally, which was that. So we're learning something from the data. Sorry for the people who saw this already this morning. So we know, heat flow is what I want to talk about, how we estimate heat flow. And a very simple representation of the relationship between heat flow and temperature or temperature gradient is Fourier's law that goes back about 200-300 years as well, which just says heat flow is proportional to the thermal conductivity, some property of the material, multiplied by the temperature gradient. So in principle, what we want to do is say, what's heat flow? That's what we're trying to estimate. So if we want to do that, we need to know the thermal conductivity, and we need to know the temperature gradient in the simplest case. And if we want to do that in the past, we need to know the temperature gradient in the past. We can solve this equation relatively simply. It's a simple equation. And we can actually have a little formula for the temperature as a function of depth, which is the surface temperature, heat flow, depth, and thermal conductivity. So again, if we know all of these, if we know the surface temperature, the heat flow, and the thermal conductivity, and the depth, if we know the temperature, surface temperature, thermal conductivity, and depth, in principle, we could calculate heat flow as well. And heat transfer in the Earth can be complicated, more complicated than the little Fourier's law I showed you. But the idea is we have heat coming from deep in the Earth. We have certain ways of transferring that heat by conduction or diffusion, which is effectively Fourier's law. You can have advective heat transfer, which can be by fluids or by rocks moving. You can have heat production by radioactive decay, chemical reactions, various other things. And eventually some heat comes out at the top, and this, depending on what happens here, this and this may or not be the same. Now, it's relatively easy to take account of most of those processes. The equations we deal with will be a little bit more complicated than the simple one I showed you before. But you know, these things like the thermal conductivity, which is not in here, but depend on the rocks, the type of rocks. They depend on porosity. The thermal conductivity can depend on pressure and temperature. We can make this problem as complex as we like. And effectively, all of these properties and even the processes themselves and the controlling heat flows can vary over time. Okay, so a classic way of trying to deal with it, or for modeling thermal histories where heat flow is important, it's in a sedimentary basin, particularly in hydrocarbon exploration, where we're trying to simulate the temperature history of rocks to understand whether we've produced oil or not. And this is a typical representation that some of us have seen this morning. The colors here, the contours are representing temperature, and the scale here is depth. So this is a sedimentary basin with burial, a little bit of erosion here, uplift and erosion, and red is hot, so the rocks are hot here and they're cold at the top. And in principle, if we know heat flow, we can calculate this and the temperature history. And if we have some data which tell us about the temperature history, in principle, we could go backwards to calculate heat flow. But the problem with this, or one thing that's a little bit difficult, is we need to know a lot of information. We need the stratigraphy to reconstruct the burial history. We need to know about compaction, porosity. If we're trying to calculate temperature, we need to know the heat flow. We need thermal conductivity. We need some equation for heat transfer in 1, 2, or 3D. And we can make that as complicated as we like. But the basic problem is we need to know many things to solve this problem. So we could calculate the temperature history if we know the heat flow history and all these other things that we need to know, but often we don't know those very well. And so similarly, if we have some constraints on the temperature history, in principle, we could calculate the heat flow history. We could estimate the heat flow, but again, we need to know all these parameters that we don't know very well. So these models are not perfect. They're like your children. So that we have problems. In principle, we can write down all the equations, and the real problem actually is the parameters we need to specify. We don't know them very well, and the data we might use, as we'll see, also are not perfect. So the idea is, can we reconstruct heat flow history over time? So we need some kind of data that tells us about heat flow, or more directly, about the temperature history or thermal history of rocks in a sedimentary basin. So there's a variety of kinds of data. I'm going to just pick a couple, but they're based on the idea that the data are sensitive to some kind of physical or chemical process, or represent a physical or chemical process that is sensitive to temperature over time. So the kinds of data that are commonly used, particularly in sedimentary basins, vitrinite reflectance, which is organic material, and the temperature sensitivity comes through breaking bonds to make different molecules, different organic molecules. And these kind of data are effectively very sensitive, or give us an indication of the maximum temperature a rock has experienced. So in a simple burial history like this, vitrinite reflectance maybe tells us here, this is the maximum temperature, might tell us something about that temperature. Other types of data, one is very commonly used in the oil industry as well. Vitrinite is very common in the oil industry, is fission track analysis, and particularly on the mineral apatite. Very different kind of data, a very different kind of process that's sensitive to temperature. But the important thing here is, because this is effectively a dating method, we have ages, we have some other information, which I won't go into, but these data, fission track data, tell us about temperature and also timing. Timing because we're dealing with something that tells us about age. Another possible type of data, which I'm not going to talk about at all, is uranium, thorium, helium, which is based on diffusive loss of helium produced by radioactive decay in a crystal. And the same kind of idea, because we're using this as a dating method, we have some idea about timing, and the diffusion itself is sensitive to temperature. So again, this method, a dating method essentially, but sensitive to temperature or temperature history. So the way to simulate these processes and their temperature sensitivity, we need some kind of predictive model, which usually, as I've written here, implies some kind of kinetic, some rate constant or variable rate that we hope we understand, but we usually don't. They're very simple, we think, certainly for something like vitrinite reflectance, which is a very complex series of chemical reactions. And the data themselves, when we make measurements, the data are noisy. Okay, so again, as we know, the data are not perfect. So models are not perfect, data are not perfect. We might as well give up. Again, a joke. Okay, so one thing, instead of worrying about heat flow, specifying a model in terms of heat flow where we need to specify things like thermal conductivity, porosity, those kind of things. These data I've just mentioned, at least some of them, certainly the fission track data and helium, are actually directly sensitive to temperature changing over time. So instead of having a model with a lot of physical parameters like thermal conductivity, heat production, we could just try and estimate directly the temperature from our data. So the way we could do that, so here's temperature, this is time. The modeling approach is, let's try and estimate what these functions look like directly from the data. We don't worry about heat flow, we don't worry about thermal conductivity, we don't worry about 1, 2, or 3 dimensions. We just go directly to temperature as a function of time. And what we can show is that if we group several samples together, say from different depths in a borehole, and we model them all together because we expect they're going to have a similar form of the thermal history, effectively in a sedimentary basin reflecting burial and or uplift at different times. And a sample near the surface, the idea is that will always be colder than a sample near the bottom. So we could think, if we could model this yellow curve, however, if we can calculate it, we can calculate these other curves which are more or less parallel if we had some kind of other parameter, which we could call a temperature offset or a temperature gradient if we know the depth. Okay, so now I'm talking about temperature gradient, and going back to Fourier's law, that was one of the things we needed to know to estimate heat flow. The other thing is thermal conductivity, which I've said we don't really know very well often. So one idea of solving this kind of problem is a quick demonstration. It's the idea we call this vertical profiling modeling with data like fission track data or uranium, thorium, helium data. The idea is we have a series of samples which can be in a valley. So this could be a valley, this is the top of the valley, this is the bottom. Maybe the valley has been formed relatively recently. So this is a bit like a borehole in the crust, or it could actually be a borehole. So we have samples at different elevations or in a borehole at different depths. We measure some data, these thermally, or data which are sensitive to temperature changing over time. So this is fission track data, this is the age, as a function of elevation, this is the mean track length, which is another indicator of the temperature, 2 types of data for fission track analysis. And the assumption we make is that these samples at different depths or different elevations will have all had the same form of thermal history, a bit like this. So when this is going up, these are all going up. When this is going down, they're all going down, and so on. So there's similar forms of thermal history, just that the sample at the bottom will have always been the hottest, and the sample at the top will always have been the coolest. And the ones in between, they will have been somewhere in between. So we can take data like that. This is just a synthetic example. Here's elevation. This is fission track age here. This would be the mean track length. And this is helium ages. And we specified a thermal history here and said, if we take these data, can we recover it, the thermal history? In fact, we do. This thermal history is actually on, you can't even see it because it's so close. There's a little line here, gray lines, which are the input thermal history. The circles here are our observed data that we generated, knowing the thermal history, and we're just saying, can we recover the thermal history we specified? And the blue lines, the solid lines, blue, red, and green, are the predictions from this thermal history. So we see we fit our data very well. And it's this idea if we have however many samples here, eight samples, we've got 8 thermal histories. They're all more or less parallel. And the top and bottom, the blue is the cold, red is the hot, are separated by some temperature difference. That's how we do the modeling. And as we know, the elevation difference between the samples, this could be equally converted into a temperature gradient. And we can let this vary with time if we want to. It doesn't have to be constant. And the idea of the Bayesian approach is that we're dealing with probability distributions. So if we're interested in this parameter, the temperature difference or the temperature gradient, we end up with a probability distribution on the temperature gradient. Okay, and in this particular case, the true value of the temperature gradient was a little bit more than 28 degrees centigrade per kilometer. This is the true value. And after the modeling, the pink histogram is the probability distribution of what is the temperature gradient. So what the data have told us about the possible values. So this is the posterior on the temperature gradient, which in this case was constant over time, but the prior would have been between 0 and 60 degrees centigrade per kilometer. So we've learned quite a lot from the data. So that's a way of estimating temperature gradient, which is half of the problem to estimate heat flow with Fourier's law. So this little study from Greenland, it dates back a long time. I had a project when I was in London with we were talking about this the other day, whether it's a company, it's a charity, or it's a university, called the Cambridge Arctic Shelf Programme. Andy Whittam was the leader of the project. Unfortunately, Andy died a couple of years ago, very suddenly. He wasn't very old. And I had a postdoc, Kit Johnson, and they worked together. And they went to Greenland a couple of times. And I think, you can't see it, there's someone standing up here somewhere. I think it's Andy Whittam. But East Greenland is extremely spectacular as a landscape. So it's quite young because it's glacial. But we have valleys, these glacial valleys that are up 1,500 to 2,000 meters deep. And quite young, because they're glacial. So what we did, saying we, I wasn't there, but these people who like climbing, like Daniel, who's there, you climb up these things and you collect rocks coming down, as we said the other day, rather than going up. So they collected a lot of rocks in these vertical profiles, so climbing up the sides of valleys, in different types of rocks. They're all relatively old. And they did fish and track analysis. Does it say that? Yeah, here. On 16 vertical profiles. And then we went back a few years later, had a master's student, Thomas Bernard, who didn't go to Greenland. He went to London to do some uranium, thorium, helium analyses, not quite as glamorous. So we got some uranium, thorium, helium data. And then later we actually measured thermal conductivities, and we'll see heat production on not many samples. And that was with Adam Schultz, who works for the Cambridge Arctic Shelf Programme still today. So just to quickly show you sort of the idea. So here we've got East Greenland, we're in here, and our study area was in here, sort of in the middle, about 72 to 76 degrees north. So you go there in summer and it's daytime all the time, pretty much, almost. This is Kit Johnson, one of the guys who was a postdoc with me, and you can see what interested him in East Greenland was salmon, not really climbing up mountains. So the yellow circles are these vertical profiles we collected. So for each of them, we had a few samples. I can't, the details not too important, between perhaps 3 and 4 and up to 7 or 8. And we did this kind of modeling of the thermal histories. And again, the details are not important here, but this is time, temperature, and these funny looking curves, thermal histories reconstructed for each vertical profile. Somewhere we have just fish and track analysis in yellow, and somewhere we have fish and track analysis and the new helium data in blue, just 3 profiles. This was published in Geology. And the thing that's of interest here today is effectively the difference between the blue and the red is this temperature offset or temperature gradient, because we know the elevation of every sample in a vertical profile. So we can take these rocks, and the way we did the modeling was this difference between the top and bottom. We said either that temperature gradient is constant over time, or we just say we let it vary. And the data tell us what they want as either a constant value or a variable gradient over time. So it went for all these different profiles. This is the profile number. It doesn't matter where they are. These are the estimates of the temperature gradient in degrees C per kilometer for the model where we keep this constant over time and where we let it vary with time. But what I've done here is just calculate the average of this variation over time. Okay, so effectively, the varying over time means the distance between the blue and red can change with time, and I've just taken the average here, and these also include the errors in the inferred from the Bayesian sampling, which I'm not going to talk about too much. Okay, so we had vertical profiles, and we class these in terms of four different rock types. 3 are mainly basement, and 1 was these relatively old sediments, color-coded here, so the gray are the sediments. And we see, I'm going to talk mainly about these variable with time temperature gradients rather than the constant. They're a bit more variable. But we see, the average value is around 30 degrees per kilometer, which is sort of reasonable, it's normal, and plus or minus 10 degrees. The variation is not so bad. We'd see that today if we went and measured temperature gradients in the Earth. That would be completely reasonable. So here we've got some values for this now, and we still need to know this. So what we did, in fact, it was quite a long time ago we did these measurements. We measured thermal conductivity on rock samples using a divided bar. I don't know if anyone knows about that. It's rather an old-fashioned way to do this. It's very slow. We just took 11 samples from these 4 different rock types, and we just said, okay, these 4 different rock types have the same thermal conductivity always. So these are based on measurements, okay? But these are not measurements. These are just the values that we measured on different rock types. So we've assigned those to our 4 different rock types defined here. So we see the sediment is relatively low. So this is 2 watts per meter per Kelvin. So about 1.8. Sediments, we've assigned that up to values of about 3.2, 3.3 for the watts per meter per Kelvin for the granite. And that is what you expect as well, because thermal conductivity is a strong function of the quartz content. And granites tend to be richer in quartz. They don't have porosity. So this is completely normal as well, these values that we get here. So the granites have high thermal conductivities. The sediments have low. The gradients are not that different. The granites will be a bit variable in the gradient, but the gradients seem reasonable. And the thermal conductivity measurements, although there's not many, but they're reasonable as well, what we'd expect for the rock types. So with that, we do this calculation, and we end up with estimates of heat flow. So again, just concentrating on the situation where we let things vary with time. You see the heat flow for most of the samples, most of the profiles is reasonable. 50 to 60 milliwatts. I think I said that this morning as well. It's sort of reasonable. It's about the average continental heat flow. So that all makes sense. And there's just a couple of outliers, or values are relatively high. So 110, 120, 130 something, 40 milliwatts, which is quite high. And it's not a tectonically active region. There's not any sign of hydrothermal activity. We're not in Iceland here, we're in Greenland. So we wanted to try and explain why could these values, which these are a couple of granites or granite gneisses, why they're a bit higher than sort of the background value of 50 to 60. So the obvious thing when we're dealing with granites is it's because of internal heat production, because of radioactive decay, uranium, thorium, potassium. So we decided to measure that. This is what we did with Adam Schultz. So Adam took some samples with a handheld gamma ray spectrometer, and you can measure the content of these radiometric elements. It's a bit approximate, but we can calculate, given these concentrations, what's the equivalent heat production. So nothing exceptional here. And we did some XRF measurements as well. Same thing, we get a range of concentrations. We can convert those to equivalent heat production. Again, nothing exceptional compared to sort of normal granites. That's just to show the distribution. You see most of the values actually are relatively low heat production. 1 or 2 values, around 3. But the heat production measurements we've got, which again are very limited, but don't suggest this is an abnormal area. So to try and understand why we get this relatively high heat flow, so delta Q is the increase in heat flow above the background of about 50 milliwatts per square meter. So we just chose some values that how could we produce an excess heat flow of 60, 80, 100 milliwatts per square meter. Sorry, this should be per square meter, not per cubic meter. I obviously copied this from there and didn't change the 3. Doesn't matter. And this is really how thick, if the heat production was constant with depth, this is how thick we would need a layer to be to explain these excess heat flows above the background heat flow of around 50 to 60 milliwatts. Okay, so our values, this is a log scale, so our values are around 2, 3 maximum. So here we're looking, even for the lowest case here, 20 to 30 kilometers of this granite thickness in 1D. Okay. There's a group of granites called HHP, or high heat production, which have much higher concentrations of uranium, thorium, potassium, which can produce high heat flow. We can measure that today in the southwest of England, in Cornwall. You see them in Australia. You see them in Norway. But we don't think we're in there. Our limited measurements sort of we're down around here for the heat production, not above 5 microwatts per cubic meter. So we might have a thickness of granites of 30 kilometers maybe, but we look for another possibility. Our granites at the best are in here, and that's probably a bit optimistic, saying 4 microwatts per cubic meter. So what we asked the question, well, could we use the fact it's not a 1D problem, it's a 2 or 3 dimensional problem, and changes in heat flow could be related to the geometry of these granites below the surface. So the idea is we have a granite here, the pink thing, which got some shape. We'll see we changed the shape, defined by a radius at the top. So this would be the outcrop on the surface. We have some depth of this granite. We have some size of this granite body at depth. So we decide to define the geometry of this by an aspect ratio, which is the height, so this, the thickness, divided by the smallest of these 2 dimensions. Okay. And for each of this, and then we've got sort of the background rocks here, the basement surrounding the granite. And we're going to assign to the granite a certain thermal conductivity. The basement outside the granite, we're always going to say that thermal conductivity is less than the granite. Okay? Because what we're trying to do is, for higher thermal conductivity here relative to there, is heat should preferentially flow into this granite, okay, in 2D. It acts a bit like a pipe, the high thermal conductivity. And also we're going to say that in our granite, we've got heat production, so H is heat production, due to radioactive decay of uranium, thorium, potassium. And outside, we have nothing. It's not really that this is nothing and this is not nothing. It's just the difference between them. Okay? And we say we're going to have heat flowing from the bottom, constant everywhere. We're going to just look at, if we took a profile of the heat flow at the surface across here, what it would look like. So just to summarize that, here we're producing heat, so we should have high heat flow above the top of this. The tendency will be for some of the heat to flow out the side, of course. So we don't expect all of the heat produced in the granite to come out the top, perhaps most of them. It will depend a little bit on the geometry of this. And also the fact this has a higher thermal conductivity than this, we expect some of the heat that's coming up here to actually get focused into the granite as well. So for different geometries, and I'm going to just talk about this very quickly, a cylinder like this, a cylinder that's wide at the top and narrow at the bottom, or the inverse, narrow at the top, wide at the bottom. This is the heat flow normalized to the background. So the background would be 1. Okay? And this is where we've got our granite with either high thermal conductivity and high heat production. Okay, so what we see over the top of the granite, in all cases, we get enhanced heat flow because of the heat production. The case like this, here, the blue, so we see this sort of peak heat flow at the edge, because what happens there is the heat flow coming from the sides, well, heat's trying to come up vertically, but it gets focused into this cone because of the thermal conductivity, so it has a higher thermal conductivity. So it sort of acts like a pipe that the heat gets concentrated and comes up to the surface. And the biggest effect is actually on the edge, as we see here. So this is the heat flow at the center of our thing, either the center of the sphere or the center of this here. And this is the heat flow at the edge. Okay, so we see slightly different shapes, but basically like this, we can have much higher heat flow associated with the granite, depending where we are and what's causing it, than we have as a background value. Okay, what's the time?
6:40 almost. That's the date, but
Okay.
60.
Well, okay, I'm just going to say that I'll skip this because it's a little bit complicated, this slide, that just those effects of the thermal conductivity, the thermal physical properties, the heat production and the thermal conductivity are actually enough, depending where we are. We don't know what the shape of these granites is below the surface, of course, but what we can see there, that's enough to explain the difference in those sort of high 130, 140 milliwatts per square meter heat flow, if we calculated, can be explained just by the geometry and the physical or thermophysical properties of the granites. So the idea of the Bayesian modeling is we can calculate these temperature histories and calculate the temperature gradient effectively and their uncertainties directly from these thermochronological data. We've estimated these values between 50 and 130, it could be about 140 actually, heat flow, milliwatts per square meter, with the higher values associated with granites and granitic gneisses, which tend to have high heat production and high thermal conductivity. But we don't have much data, so if we really wanted to take this further, which I'm not sure we do, we need more thermal conductivity measurements, we need a lot more heat production measurements, and maybe something like gravity data to try and define the shape of the granites below the surface, because there's also density contrast. Okay, that's part one. Ready for part two? Should we have an ice cream? Okay, I'll try and go a little bit faster. So I'm going back now to this, this idea of the sort of sedimentary basin case, because it's important in the oil industry. It's something I've worked on for quite a long time. Trying to solve this sort of thermal modeling problem. As I said, there's lots of stuff we don't know. Trying to solve that as an inverse problem. So generally what we do is specify the heat flow. We make these calculations. We compare our predictions to our calibration data, so the vitrinite reflectance or fission track data, and say, well, we can fit the data with this certain heat flow history or not. That can take a lot of time. It's often a little bit subjective. So since before you were born, some of you, I expect, you know, I was 3 years old when I was working on this. We've looked at different ways of sort of trying to solve this problem as an inverse problem. And back then, in the previous century, we used a sort of relatively classical inverse approach. And more recently, we've looked at this Bayesian transdimensional Markov chain Monte Carlo, and the previous stuff I spoke about was actually the same. And this just reminds me to say a lot of this work was done by Andrea Licciardi, who was a postdoc with me in Rennes a couple of years ago. We had a project sponsored by Equinor, the Norwegian oil company. And he's there because it was him who paid for everything. He didn't really do anything, but that's how it is. So I'm just going to try and quickly go through what we did. This is the kind of equation we have to solve. I think someone asked me this morning, was my equation too simple? So this is the kind of equation we solve in this case to try and allow for lots of different physical processes, the little cartoon I showed earlier on. It's still just a 1D problem, the way we're solving things, which I think is okay. But a lot of these parameters, as I said, depend on the rock type, they depend on porosity and so on. But we can make assumptions about those. So we can solve an equation like that with no problem numerically. And the things we're interested in general, in an inverse problem in this case, is for the model, we'd like to know what the model parameters are and what their uncertainty is. We'd like to know, are they correlated? If I change one parameter, does it change what I would say about another parameter? And we'd like to know the effect of what I call nuisance parameters, or it's not just me who calls them nuisance parameters, they're parameters that we need to specify, but we don't really care about. And this can be things like the uncertainties on the data. We spoke about this at great length, I think, earlier this week. And some parameters like these things like thermal conductivity, compaction, how we deal with compaction, the magnitude and timing of erosion. Sometimes we don't really care about those, but we need to know them to do the modeling. Okay, and for the data, well, I've already said the data errors. We don't often really know those well enough. We'd like to know also which data are important, which data are controlling our solution, however we get it. And we'd like to know when we combine different types of data, which types of data are more important than others. Okay, so the approach we use, and this was in Journal of Geophysics, I think it's 2020, is we have our observed calibration data, things like vitrinite reflectance or fission track data. We might have porosity measurements, either direct measurements, it's very rare, but often porosity from logging down holes and boreholes. And the things we need to specify are sort of geological things like the stratigraphy, something about erosion if we know that, when erosion occurred, how much erosion there was, how much is missing, perhaps the present day temperatures we need to know, and something about the lithologies to define thermal conductivity and heat production, all that kind of stuff. So we need this even for a forward modeling approach. We need to specify all these things. These are the things I said we don't really know very well often. We can simulate the burial history where we allow for the fact that sediments compact and change their thickness because of porosity changes. We take our little heat transfer equation, we can combine that with the burial history, we can calculate the temperature history, then we can solve these chemical reaction equations or annealing for fission track, whatever, and we can make predictions of these things that we can observe. So the idea is we have predictions of these, we compare these. And the inverse problem is to deal with this, is to go back and say, well, we've chosen a heat flow, Q, the heat flow is a function of time. We do all of this with that value of Q. How do our predictions compare with the observations? Are they good or bad? And we keep going in a big loop until we decide we've had enough and we stop. And at the end, because it's Bayesian, we get a posterior distribution of things like the heat flow over time and lots of other things that we might be interested in. For example, the erosion timing and magnitudes. Maybe we are interested in those, maybe we're not. And these things are called hyperparameters, which are things like the data errors. Again, so the stuff we're not really interested in, but we need to know them. And so sometimes we might need to know what's the uncertainty on those parameters. It could be the thermal conductivity, it could be compaction coefficients, those kind of things. So stuff we're not that interested in, but we need to know them, so we might as well estimate them perhaps as part of the modeling process. So the way the modeling is done, I might skip that, and just show you a quick example. So this is a heat flow history, so time coming towards the present day here. It's very artificial. So we just have a big increase in heat flow and a reduction in heat flow. This was our burial history, so a very simple burial, blah, blah, blah. And just the blue lines are where we predict, we say we have fission track data, so we make a prediction for those thermal histories for fission track data. And the red are where we say we have vitrinite reflectance data. We make a prediction for those thermal histories associated with those burial histories. And the thermal histories, when we combine this and this, are here. So a very artificial example. What we see, we have a maximum temperature here for most samples, certainly at depth, except for the samples near the top where their maximum temperature is sort of going towards at the present day. Okay, so we look at that and we say, well, what would any data we could measure in a borehole, these kind of things we might be able to measure, what would they tell us about this? And then what could we say about this? Can we recover this sort of strange hat-shaped function? So this is just an example of, say, the vitrinite reflectance we might predict with this thermal history based on this burial and this heat flow. And the idea is, can we take this and go backwards to recover that? So we do this both with and without the fission track data. So we'll just see the difference, I think. So this is the reconstruction of the heat flow history based just on the vitrinite reflectance data. So here we've got heat flow, so from 0 to 250 milliwatts per square meter. That's high heat flow. So we chose this. This is in fact the prior. It's the range we said is possible. and this is geological time. So we used our data with the burial history and blah, 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 to try and invert the, or try and estimate the heat flow as a function of time. So this is the true model in white. The colors sort of indicate more probable, so red is more probable than blue. And we see what we get with just the vitronite data. We get this sort of thing which just says heat flow increased back up to more or less the maximum value we have in the white curve. And this black line is the model that fits the data the best. And again, some of you, we spoke about this before. We said this is actually relatively complex. But the part of the model that's well constrained, this maximum likelihood model, is similar. So that the red color, or the colors, is the posterior related to the number of models that pass through this region. Okay, so think of it as a probability, if you like. And this is the case where we add in the fission track data. So it changes a little bit. We see sort of this part is well resolved. We actually get a better resolution of this rapid change when we add in the fission track data. And the reason for that is because this sort of maximum temperature, about 40 million years, is in here. And the fission track data, because they give us information on age or timing, they tell us about that 40 million year thing. So the fission track data actually give us information about when this occurred. The vitronite data don't really care. All they need to do is get to this temperature, maximum temperature, at some time. They don't really care when it is. Okay. And the other thing I've written up here is, in fact, the resolution on this, as we go back in time, the resolution decreases, and particularly decreases after the time of this maximum temperature. So even with the vitronite reflectance, we don't actually resolve this step. We're about the right value here. The white curve and the color, the red colors, is about this point here. And it's that's important for explaining the vitronite data. Just get to that temperature. And it's about the right time. And the fission track data more or less the same. But we see as we go further back in time, as the temperature history is actually much lower, what we understand is that the data don't really tell us much about temperatures prior to the maximum, particularly vitronite data. So what we see in the posterior, this is our recovered uncertainty on the heat flow history. It can go anywhere. So all we're doing there really here is we're recovering the prior. It's what we said we thought was reasonable with no data. So the data, the fact we recover the prior here, says the data tell us nothing that we didn't think we knew already. And we see that sort of the width of this recovered posterior approaches the prior as we go back in time. But by the time we get to here, the data tell us absolutely nothing, because we're at temperatures, very low temperatures here. The data can't tell us anything about those temperatures. Okay, and another little thing is the sort of trade-off between increasing heat flow and having erosion. So just very quickly, it's 26 degrees. What time is that? I'll translate that into a time. 46 minutes. Let's go. We'll get there. So this is, again, just a simple forward calculation. So if we had a heat flow history that did this, we have a sort of spike, and then it's constant. We get a thermal history that, sorry, I should have said for the same a simple burial history here. This heat flow spike gives us a sort of spike in the temperature, okay, around that time for the sediments that were deposited by this time. Okay, so it's a bit like the example we just saw, an increase in heat flow here. Maybe the data can tell us something about the magnitude of that and the timing. But similarly, down the bottom is a model where the heat flow is constant over time. And we just have, in fact, a period where we have extra burial and then erosion. So things get hot and then get cold again, but that produces much the same effect. And so the question is, can we tell the difference from the data? And it's going to be difficult because they have a similar thermal effect. And so what we'd expect to measure in the calibration data that are sensitive to temperature, we'd expect to see much the same thing. So let's go to Norway, northern Norway. So this was part of the project we had with Equinor. So this is Norway here. We're up here near the Barents Sea. You see how close Russia is to Norway. That's why Norwegians are worried. Sweden, Finland, all a bit worried. And it's quite an active area. All these little red circles are wells. We're going to just very quickly consider 3 wells. This map is a map of estimates of erosion. So in these boreholes that we see there now, almost at the seabed, it's sort of Jurassic or Cretaceous rock. So there's a lot of stuff missing from the top, is the idea. Okay. It depends where we are. So the colors are, blue in here is high erosion up to 3,400 meters, and red is not so much erosion, a couple of hundred meters maybe. So we'll look at this well as a well with not much erosion. Then we'll look at these 2. I can't remember which order they're in. And one way, something we can do with porosity data, I didn't talk about this with you before, I think, but porosity reflects compaction. So as the sediment at the surface is quite porous, as it gets buried, it gets compacted and the porosity reduces. But if that layer of rock between my hands goes up to the surface because of erosion, it stays compacted, it doesn't expand. Okay? So the porosity at the surface would be low compared to what we'd expect if the rocket had been submitted to a lot of erosion, a lot of missing section. So the idea of using porosity, typically porosity, we parameterize something like this. It was very simple, that porosity phi here as a function of depth is some kind of exponential decay. And that's sort of what you see in the data often. And we have 2 parameters. We have porosity at the surface here, and this constant C tells us how quickly the porosity decreases with depth. Okay. So to simulate that, we need to know these 2 parameters. And they might vary with lithology, blah, 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 all that kind of stuff. So the idea of trying to estimate erosion from porosity said if we could define some reference curve in a place where there'd be no erosion, and we go somewhere, so a little bit, we're over here where there's not much erosion, and then we go over here, and we measure porosity in our well, and maybe we have data that looks like this. So at this depth of 500 meters, from our reference curve, we expect porosity to be 40%. But what we actually measure is more like 10 to 15%. So the idea is that's been buried more deeply, and then this erosion and that whatever this layer is has come up to the surface. So the idea of estimating erosion from porosity data is just, if we have these data, we just said, how far do we have to move them down till they intersect this reference curve? Okay, so porosity data can be useful. They're not really dependent on temperature, unless we've got sort of problem processes like dissolution or cement forming, changing porosity. If it's just mechanical compaction, should be relatively independent of temperature. So here's this well with some data. The well sort of that was to the left where I said there wasn't much erosion. So this is sort of our reference curve in this part of the world for porosity changing with depth. And so we estimated these parameters, the phi 0 and the C, using Monte Carlo, Markov chain Monte Carlo. And just to show sort of how that does, is this was our prior, say for the surface porosity, so between 0 and 100%. And this is the compaction coefficient C. So we said the values can be anywhere in these light blue bands. And when we calibrate against the data, this is what we get for the posterior. So we learn a lot about the good values for those 2 parameters. And also those 2 parameters are correlated. So this is the surface porosity phi 0 against the compaction constant C. We see they're very strongly correlated. Okay, so we can change one of these, and provided we change the other one to respect this correlation, we'd get much the same effect. Okay, but we've defined what these parameters are rather than just taking one value for each. We're saying let's use this information, let's use the probability, such as the posterior, let's use that when we're modeling somewhere else. Okay, so we took another well, this is the well which was, I can't remember, 22, this one here, I think, 2211. Sorry, I had the plot again then. No, it's this one in here, which according to this map has experienced a lot more erosion. And we use this compaction approach here to estimate how much erosion there might have been in this well. So again, the prior, we said it's anywhere between 1 and 5,000 meters. The data, it's just on porosity measurements, tell us it's sort of 2,500, 2,400. Okay. And another thing we did here, this is one of these nuisance parameters or hyperparameters, is actually how we might rescale the errors on the data. So if the data are too precise, then we try to overfit them, and we can get sort of a bit confused as what's a reasonable model. So one way of dealing with that is to say the data are not as good as we think they are, and let's find out how not good they are. So this is a scaling factor that multiplies the input errors on the porosity by this scaling factor to try and find a more consistent model for all of the data. Okay, so this is again a nuisance parameter. We don't really care about that, but it's useful to try and be able to estimate it. So these are the data that we fit, and if you look here just on the scale at say 1,500 meters, we're at about 0.05, 5% porosity at 1,500 meters. If we go back to this is our calibration well, 1,500 meters, we're at 20% porosity. That's the idea. We've got this reference curve of normal compaction. We go somewhere else, the porosity is much lower for a given depth. We can try and estimate how much erosion has been, how much extra burial. And because it's Bayesian, you get a probability distribution on that. And so for the heat flow, for this well, we get something that looks like this, based just on vitrinite reflectance and also some fission track data. I can't remember exactly what we had as data, but just these data that are sensitive to temperature. And we saw already there was that little trade-off between erosion and heat flow or temperature. So, whoops. In this case, we have to try and estimate heat flow and the amount of erosion. Okay, so this is our estimate of erosion. We also have an estimate of the start and end of the erosion event. So we don't know that very well. I wasn't very clear when I said that, but there's sort of a gap of maybe 130 million years at the surface. So there's what you find that near the surface is late Jurassic, early Cretaceous, and then nothing. So we don't really know. We just know something's missing, but we don't know when it was eroded. So what we try to do is, with the thermally sensitive data, vitrinite and fission track, estimate the heat flow and the amount of erosion, as we've seen as a bit of trade-off. We get some information about the start and the end in millions of years of this erosion event. If we add back in the porosity data, which he said told us something independent of the thermal history about erosion, which was a bit more. So here using just the thermal data, the erosion is sort of a bit over 1 kilometer. When we include this porosity data, we get to a value of about 2 kilometers, and the heat flow changes a little bit. And again, the timing of the erosion changes a little bit. The end is more or less the same. It seems to be very young. I said there's nothing on top. In fact, there's very thin quaternary sediments on top, so we know it's quite recent, the end of erosion. So different answers depending on what assumptions you make, but clearly the porosity data here adds something to the thermal data. And so these are the two, with the porosity data and without the porosity data. So things change a little bit, and we can make a decision which one we prefer, perhaps based on some additional geological information. And we're doing this just on one well. And what you probably want to do is do it on 30, 50, all the wells that we saw on that map, do them all together and get something that's consistent regionally. Very quickly, I'm almost finished. This other well, which was here, this is just very quick because it's the same idea. We've got fission track and vitrinite data, I think, trying to reconstruct the heat flow history. And this is just showing an example. Sorry, the quality is not great here. It looks like I took a bitmap of something. But this is the burial history. And this is the thermal history that's associated with this burial history and this heat flow history. So remember, that's how we can calculate temperature. And again, we didn't know the duration of this this unconformity when erosion starts, how much was missing. We didn't know that in advance. It's something we estimate, again, around sort of 1.5, nearly 2 kilometers. We get the timing, start of erosion, sort of this time, and the end of erosion. And here we're just showing one model. In fact, it's the model based on this black curve here. But clearly there's uncertainty in this timing here. There's uncertainty in the magnitude of this erosion. But we quantify that with this approach because it's Bayesian and we get posteriors on everything. I'll skip this because I can see your eyes. And just to finish, so the second part was this idea of modeling heat flow in sedimentary basins. So we can use as much data as possible, seems to be good, that tell us different things. So the vitrinite and the fission track, vitrinite tell us about maximum temperature, fission track tell us about temperature and time, porosity tells us something about this erosion if the compaction model is correct, which may or may not be. The difficult thing there is to define that reference curve where there's been no erosion. We don't really know how best to do that. But if we can do that, and we have those kind of data in this Bayesian scheme, we can estimate the model, the uncertainties in some of the parameters, like they're the erosion magnitude and the timing are parameters we need to solve the forward model. So we need to know those, but we might not know them very well. And the data, in fact, we can use them to estimate their own uncertainties. We saw that sort of the scaling factor that says actually the data are not as good as we thought they were. So we can estimate, in fact, the errors that give us a more consistent model. I didn't talk about this as one of the slides I skipped. We have a very flexible parameterization for heat flow history. So it can be anything if we want, which is not always a good thing to do, but it can be anything. In contrast to the things we did in the past, and I said before most of you were born, we were using these quite classical geophysical inversion methods based on gradients to say, if we change the data predictions, we need to go in this way to fit our model better. And those depend on our starting model because we need to calculate a gradient, a derivative of heat flow with respect to vitrinite reflectance, for example. So the Bayesian Markov chain Monte Carlo approach doesn't depend on starting models. And the really nice thing is we get all of these uncertainties as probability distributions, and sort of for free, we get the correlation, the covariance, how all the different parameters are related to each other. If we're interested in seeing that, it's very easy. And the prior, which I said, that example with the heat flow, we assumed a very wide prior up to 250 milliwatts per square meter, which is probably way too large. But we can change the prior as we like. So we could have a different width or values of heat flow possible at different times. It's up to us to decide how we do that. We choose the prior. We can also have models. In fact, we did that. I didn't show any of it, but to allow for sort of conceptual models like the famous Mackenzie model for extension, where we expect high heat flow early on in the basin and then it decays with time because we're losing heat from the lithosphere, often used to explain extensional basins and passive margins. We can deal with the model of that form. We can say we want something that does that if you want to. And we did it, but I didn't show it either. So I think that's the end. Really 10:13. Okay, so thank you very much. I know I went a bit fast. I'm exhausted. Okay, well, if you have any questions or... Good.
The data for porosity only works in silicate rocks or maybe carbonates?
Carbonates are really difficult because I think there you have a lot of chemical alteration, you have dissolution and secondary porosity, you have cements, so carbonates. There is one study which was done by Peter Japsen, a guy in Denmark, who in the North Sea, where he looked at chalk. And he compiled a lot of data and he was very careful trying to sort of filter the data. And he published a very nice paper in APG Bulletin. But since then, a lot of people said, why do you use chalk? It's full of sort of chemical reactions and stuff that changes porosity that we don't really understand. So what we showed there was based mainly on shale, those sort of reference curves. But in the study we did with Equinor, and it's published in the paper, I think that we published in JGR, is we used we used sandstone, siltstone, and shale, which are the main rock types. So it's up to you. I don't think we could define a reference curve for sandstone, so I think we made it up, which we shouldn't do. We took some values from a book. That was a study in the North Sea, which is about 1,000 kilometers away, so it's not necessarily a good idea to do that. But we didn't have enough data from sandstone to calibrate the compaction model, or at least not where we thought there was an erosion.
Kerry, thanks for the very nice talk. I have a question on the data in Greenland. So you are estimating the temperature gradient, and then with this you calculate the heat flow. So this heat flow is a heat flow for how long?
Well, yeah, that's a good question, and I can't answer it. So the idea of letting the heat flow vary with time, there's not really a sense in these diagrams, and I'm not sure these. Did I have a pointer? Oh, it's a stick. So in these things, it looks like from here that this temperature gradient or the temperature offset is constant with time, apart from when we come to the surface. But sort of looking back here, these look to be constant with time. But the idea in the model approach is with something like this. So we define a temperature history as a series of points that we join up with a straight line to make a continuous function. And for every point, we'd say there's a different temperature gradient. So it depends where the points are. And the points move all the time, and sometimes they get deleted, and sometimes we add new points. So it's very hard to say when it's changing. And I must admit, we've never looked to see, does that tell you anything about sort of rifting at all? We didn't look there.
So the values that you got that require heat production in these gradients with these shapes are heat flows, present day heat flows.
Well, yeah, I said that quite quickly. I just took the average.
Average?
Yes, so I took the average, whatever they were doing over time, I said just take the average over time. But the uncertainty, where you see the error bars, tend to be smaller than the case where we said it's constant. Because in fact, you always fit the data a bit better when you're letting more things vary. So we're letting that parameter vary with time, and we tend to fit the data a bit better. So the sort of predictions on the data are better as well. But because we don't really know when what the time variation is, because everything's moving, the points are moving in time, and sometimes, I said, sometimes being deleted. I just thought, well, let's take the average over time. They didn't vary by a great deal. Sebastian?
Yeah, I have a question from the same figure. In this model, when you fix the thermal gradient, what will be the driver for this very high values? If you go to the left. So when you fix the thermal gradient, you get really high.
Yeah, I think it's trying to fit the data, and the fact these can't change with time. So it might be just one part of the thermal history is important. What numbers are they? 19, 3, and 8. I can't see which ones are. Glasses don't help at all. 3, or 3 is here. So something like this. Maybe you see. So this is just the difference between I think there's probably only 2 or 3 samples in here. So it depends. The difference between the red and blue lines depends on their actual elevation difference today, and we assume that didn't change over time. But you see here, it's sort of very close. And then when we go back to here, we have this thing. And then prior to that, it's very uncertain. And maybe in here, if you had a variable temperature offset or temperature gradient model, that might change. So I can't really give you a good answer, as you probably can judge. But I think it's just the fact we constrain the temperature gradient or the temperature offset has to be constant with time, and that's a bit too rigid. I think over whatever time scale this is, 500 million years, I think. Probably don't expect that to have been constant all the time. So I don't really know why, but that would be the model in a way with a constant gradient over time is too simple.
Yeah, in the second example, these heat flow variations that you see are surface heat flow or heat flow at the base of the
heat flow at the base, yeah.
At the base of the basin. basement?
I can't quite remember exactly what we did. The code was written, so you could say where you want that boundary condition to be. So it could be right at the base of the sediment, or you could put it at 100 kilometers below. It's up to you, and I can't remember what we did.
Just my question is just because of this, because if you think that these are heat flows at the very base of the crust or the lithosphere, there will be a time for the conduction of heat.
Exactly, yeah.
And so these drops in the heat flow will be, if we are going to try to find the trigger of this, we should think about things that happened several tens of years before that, right?
Millions of years, yeah.
Yeah, tens of
Potentially.
years.
But these do correlate, and the sort of thing that slightly worries me, and normally in public we don't say the things that worry us, we hide all that. But what we tend to see here is that this heat flow sort of, well, if we take a look at the black curve or even sort of the colors, they're doing much the same thing. You've got high heat flow, and this is the heat flow at the beginning, sort of around 80 milliwatts. And then it decreases, and then it comes back up again. And the minimum is around 80 million years. And in a way, that's exactly what I think what you're thinking about is, I think I said this morning, when we put sort of sediments on in our basin, if you put them on fast enough, they're cold, and they take some time to heat up. So the heat flow, at least on the surface of the Earth, would decrease. So we'd expect something like this. We've got this sort of rapid sedimentation, perhaps not over such a long period, but we'd expect heat flow to go down, certainly perhaps here, and then come up. So around 80 million years is where we get this minimum. And the fact it increases is the opposite effect, that we've got erosion and stuff is coming up to the surface in a way relatively fast, which could be transporting heat. So that does something we would think is physical, but it does depend, as you say, where we put that boundary condition. So what this heat flow is. And I think it's the heat flow at the base of the model, not at the surface. And I think that boundary condition was put maybe 5 or 10 kilometers below the sediment. So not really, really deep. But the thing that worries me, if I can, I'm speaking freely, this won't go outside this room, is that correlates, this minimum almost always correlates with the maximum burial time. And as we saw, well, maybe I even have another little slide somewhere just at the end. You shouldn't have asked that question. I think I put in one here that decided something like this. So we can't read it again. It's a sort of bitmap, but this is the erosion event, a thickness of erosion, small to high, and this is heat flow at the time of erosion. So you see that they're strongly correlated, and this is just two different models. I can't quite remember what they are. But as we increase the amount of erosion, we decrease the heat flow because those two things trade off almost exactly. So you might want to try and build in some prior constraints, not let the heat flow perhaps change as much at that time of erosion, which is easy enough to do. But I think that increase in the heat flow is just reflecting some kind of trade-off here, which if you want, and the way I would approach that is to say, let's just say heat flow is constant. How much erosion do we need? And that will give you a maximum amount of erosion. Then you say there's no erosion. We've got an unconformity, but there's nothing missing. Okay, they're very extreme assumptions. But then what's the heat flow going to do? And then you'll get another extreme model. But the thermal histories will probably be the same or very similar. They'll be like the thing we saw there, whatever it was. I showed the trade-off. That. So here, that's sort of very different mechanisms. However much erosion there is here, kilometer and 1,200 meters or something, but these give pretty much the same maximum temperature. And it just depends what the data can tell us about that, and often they can't tell the difference, unfortunately. Can I stop now? No questions from anyone outside?
Thanks a lot.
Okay, well, thanks again for muito obrigado. And have a good evening.
That's it. Thank you.
Thank you.